Atomic structure and bonding. Ions. Ions are different from atoms as they contain the same number of protons and neutrons as an atom of that element, but they've either lost or gained an electron or electrons. This means they have an overall positive or negative charge, whereas atoms have a neutral charge due to having the same number of protons and electrons, so the charge balances out. Positively charged ions are called cations, and negatively charged ions are called anions. Bonds between atoms always involve the outer shell electrons. These electrons are often shared or transferred. Noble gases have a full outer shell of electrons, which means they have a stable configuration and they are very unreactive. When atoms bond, they aim to achieve this stable noble gas configuration. The three types of chemical bonds are metallic, covalent, and ionic. An ionic bond is a transfer of electrons. Metals have 1, 2, or 3 electrons in their outer shell, and they often lose these electrons to achieve a stable noble gas configuration. Non-metals often react to gain these electrons also to achieve a stable noble gas configuration. Ionic bonds are between metals and non-metals, electrons are transferred, and positive and negative ions are formed. The attraction in the ionic bond is created by the very strong electrostatic force of attraction between negatively and positively charged ions in an ionic lattice. Magnesium chloride contains Mg2+ ions and Cl- ions. Because chlorine only has a 1- charge, we need 2 of them to balance out magnesium's 2+ charge. This is how we can figure out that the formula for magnesium is MgCl2. Sodium chloride has ionic bonding as well. Sodium has 11 electrons and chlorine has 17. The outer electron on the sodium atom is lost and gained to the outer shell of the chlorine atom. They are now charged ions with full outer shells. Ionic bonds are the result of electrostatic attraction between these charged ions. Each positive ion attracts a negative ion and each negative ion attracts positive ions, multiple of them. This is why ionic compounds form lattices. Properties of compounds with ionic bonds. Ionic compounds are solids at room temperature. They have high melting points due to their giant structures. In order to melt an ionic lattice, a lot of energy is needed to be supplied to break the lattice of ions. Ionic compounds are conductors of electricity, but only in states when they're molten or dissolved. This is because the ions that carry the charge, when they're in a solid, they are in a fixed position in the lattice, so they're not free to move around and carry the charge. However, as a molten or liquid state, dissolved state, they are free to carry the charge. Ionic compounds are brittle and they shatter easily with a sharp blow. This is because a sharp hit to the ionic structure can knock the lattice out of place. The lattice is held together because of the positive ions being attracted to negative ions and the negative ions being attracted to positive ions. Sometimes with a sharp blow to an ionic lattice, this can slip out of place. So then the positive ions are surrounded by other positive ones and negative ions are surrounded by other negative ions. So there is no longer this attraction. Covalent bonds. A covalent bond is a shared pair of electrons. For example, chlorine gas exists as pairs of Cl2. The 2 chlorine atoms share a pair of electrons, so each atom now has a stable noble gas configuration. Covalent molecules or structures have a neutral charge because there are no electrons lost or gained, only shared. Double covalent bonds exist where 2 pairs of electrons are shared, for example in carbon dioxide, where each oxygen atom shares 2 pairs of electrons with the carbon atom. Double covalent bonds are represented by a double line, whereas single covalent bonds are represented by a single line. Sharing electrons is what holds atoms together in covalent bonding. This holds the atoms together due to the electrostatic attraction between the nuclei and the shared electrons. In the example of hydrogen, the hydrogen molecule is held together by 2 protons and a pair of electrons. The forces, as shown in the image below, are balanced out when the electrons are at a particular distance from the nucleus. Dative covalent bonding, otherwise known as coordinate bonding, occurs when both shared electrons in a covalent bond come from the same atom. An example of this is an ammonium ion, where the nitrogen atom shares a pair of its electrons with a H+ ion or a proton. Dative covalent bonds are represented by an arrow. Dot and cross diagrams. Dot and cross diagrams can be used to display and visualize covalent bonds. The dots and crosses represent electrons on respective atoms, and these diagrams make it easy to visualize which electrons are shared. You can see examples of these that I have drawn here. Electronegativity is the power an atom has to attract the electron density in a covalent bond towards itself. Fluorine is better at attracting electrons than hydrogen is, which means fluorine is more electronegative than hydrogen. Electronegativity depends on the nuclear charge, the distance between the nucleus and the outer shell electrons, and shielding by electrons that are between the nucleus and the outer shell electrons. Polarity of covalent bonds. Polarity occurs when there is unequal sharing of electrons in a bond. When a covalent bond is between 2 atoms of the same element, these atoms have the same electronegativity because they're the same element. So the electrons in the covalent bond are shared equally. However, in instances of covalent bonds between 2 different atoms, these will often have very different electronegativities if they're different elements, so the electrons will not be shared equally. For example, as mentioned before, fluorine is more electronegative, better at attracting electrons than hydrogen is. This means that in covalently bonded hydrogen fluoride, the fluorine end of the bond attracts the electrons more and therefore is delta negative, and the hydrogen side is delta positive. This creates polarity in the bond.